Hello class, I'm going to walk through the week 5 group homework assignment. I filled out much of this already ahead of time, so I'm just going to make some comments on the solutions as we go, and then some problems I've left unfinished so we can finish together. Number 1, according to boxofficemojo.com, the movie Avengers Endgame grossed, and then this digit here with a dollar sign in front, worldwide. Do the following. Express this amount of money in words. So this is quite a large number, and the 2 is in the trillions position. The 7 is in the hundreds of millions, the 90s of millions, or the tens of millions position, the millions position, etc. So in the end, using nothing but spelled out numerals, we have 2,797,800,564. And this, of course, would be measured in dollars, as opposed to, say, Japanese yen or some other amount. So I should probably, in my description here of this amount of money, unless you put a unit on here, then ultimately a number is meaningless, if you recall earlier discussions we've had. So let me put the word dollars here at the end to give it meaning. Question B is identify the object, quantity, and value of quantity as these terms are defined in the lecture. So the object is a thing that we're thinking about, and it doesn't have to be a tangible thing. So the word object sometimes is misleading. Some people think it has to be like a brick or something you can actually visualize or hold. Sometimes the object is an idea. It's a mental object. And in this case, the idea of the movie is the object we are contemplating. And it has a measurable attribute. The attribute is how much monetary gain did it gross. How much revenue, in other words, did it take in. And that's measurable because we can establish that value in some unit such as dollars or yen or euros or some other unit of monetary value. But that's the quantity. And so I can think about the movie and its value as far as its revenue is concerned, and without actually measuring it. So we've got an object and a quantity. And then the value of that quantity, of course, is the numeral with its unit of measure. So in this case, that 2 trillion figure that's measured in dollars. So this one here, there's obviously lots of answers for the next part of this question that you could find and give an example of a number that is relevant to our society, and that is between 100,000 and 1 million. So I went to Google and I just started looking up interesting things. And on Google, I discovered that the distance between the Earth and Moon is approximated to be 238,900 miles. So that was between 100,000 and 1 million, so I went with that. I expressed that value in words, included the unit of measure right here. And the object here, so there's actually 2 objects you might think in our thinking. There's the Earth and the Moon. But even a collection of objects could be regrouped into a singular object. So I'm calling the object this Earth-Moon system, right? A collection of things could be the object of your focus. It doesn't have to be a singular thing because you can group them and think of them as think of any collection of multiplicity of things as a singular object. So my object is the Earth-Moon system. The quantity is the distance between the two. That's something I can think about without actually measuring. And then the value of that quantity, if we measure it using miles anyway, that value is 238,900 miles. The reason I like these examples is because they help establish how I'm thinking of the word quantity and how I'm going to use it in our class in a way that is perhaps different than everyday usage. Because most people, when I say, give me an example of a quantity, they will tend to give me an empty numeral like this and say, that's a quantity. So I'm pushing back on that just some random number is what we're going to be calling quantities. I'm going to call numbers numerals, and you put a unit on a numeral, then we have a value of a quantity, but the quantity is the more abstract thing that doesn't need to be measured in order to be thought about. In this case, the quantity is a distance between 2 planetoids. Let's now go to the next one. Question number 2. Use base 10 blocks to perform the following operations. Feel free to draw simple representations of the required base 10 blocks and explain your steps. So I've begun by drawing these bars here are the 10 blocks, and then these dots are representations of the 1 blocks. So when I have 35, I have 3 10s and then the 5 1s. Now when you're doing a subtraction model, I'm going to do the takeaway model for subtraction. So I'm going to just start with the minuend, which is 35, and we're going to remove from that the subtrahend, which is 17. And I want to remove the 17 in pieces. I'm going to remove 7, and then I'm going to remove 10. Well, the problem is with our base 10 blocks is that I don't have 7 1s to remove from. I only have 5. And so this is where we do the idea of borrowing. I'm going to turn this base 10 block right here into 10 1s. So let's do that now. I'm going to just delete it and replace it with 10 1s. Okay, so there's my 10 1s. So this still represents a value of 35. But now I'm in a position that I can remove the 7 and then remove the 10. So now we're going to highlight the 7 that will be removed. I can remove these 5 plus 2 more. And let's, I'm going to color these a different color, or you could just circle them in your own work and say remove these. But I'm going to remove everything that's red. So those are the 7 that are going to be removed. And then I also need to remove 10, right? Because to remove 17 is equivalent of removing 10 and then removing 7 in either order. So I need to remove one of these base 10 blocks as well. So I'm going to just color it red. And then we have this idea that everything that's red needs to be removed. So it's going to be taken away. And what do you have left? Well, we have 1 10 block and 8 1 block. So 18 would be left. So maybe in my notes I would say something like this. Remove the red, and that leaves, and then I'm going to copy and paste the black so I can have a visual representation of what's left. So this justifies that the result is 18. In the case of addition, I did a representation for both numerals. The 176 has its own representation using base 10 blocks, and the 42 has its own representation using base 10 blocks, and I'll use the combine idea. So we just combine these into one numeral and try to say what's my new numeral. And combining the ones, we have 6 1s and 2 1s, so those combined to just be 8 dots. No need to convert any of these dots into base 10 blocks. But look how many base 10 blocks we have. Recall that if ever we have 10 of one object, then we want to collapse them into a single object that is one step higher in magnitude. And so I'm going to convert 10 of these base 10 blocks. Well, here's 7 of them plus these 2. In fact, I'll color them green just to make them, stand out in our thinking. 7 plus the 3 make the 10. I think let's double check this, make sure I have in fact colored 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, yes, so those 10 will, we're going to convert to a 100 block. So now we're going to have, the result will be something as drawn below. We have the 100 block that we already had to begin with, but we've created a second 100 block out of the 10 blocks. And then we had a single 10 block left, and then we had the 8 single blocks. So this justifies that the result is a value of 218. Use place value tables to perform the following operations. So I'm going to do subtraction with dots and addition with numerals in my place value tables. If you're looking at a representation for 73, then we need 7 10s represented by 7 dots in this block, in this portion of our table, and then 3 1s represented by these 3 dots. And we're going to remove from that 59. So there's 5 10s and there's 9 1s. Now we want to arrange these dots so that above any box in the second row, so looking here at the second row, above each box in the second row, we want more dots above it in the first row. So currently, we have 9 dots in this box here in the second row, but only 3 dots right above it. I want to get to 9 or more above it, and I'm going to have to do this by borrowing, right? So I'm going to take one of these dots. I'm going to highlight it, make it red. Do it this way. Oops. And I'm going to convert it to 10 dots in the 10 more dots in the ones position. So maybe it's hard to do a dynamic unless you draw this grid multiple times to show your steps. If the challenge for you in your work, of course, is to explain what's happening. So you could explain what's happening in words, or you could, some other options you might have at your disposal would be, right, to draw multiple representations of this and to show how it transforms as you make different changes. This video, I'm going to let it suffice to do my dynamic changes dynamically, and leave it to you the challenge of expressing what's happening. So I erased one of the dots from the tens position, and that allows me to put 10 more dots in the ones position. So now you should see that we have 60 tens and 13 ones. So we still have a value of 73 up here. But I'm now in a position now where the number of dots in a box in the second row is now less than or equal to the number of dots in the boxes above, and that's true for both place value positions, the tens position and the ones position. So now I can just remove dots. So I have 13 single dots here, and I want to remove 9. So if you have 13 and you remove 9, that's going to leave 4 dots in the ones position. If I have 6 dots here and I have 5 dots below it, I want to remove 5 dots from 6 dots. That leaves 1 dot in the tens position. So this leads to the conclusion that what's left is 10 and 4 ones. In other words, 14. Okay, for this problem, 125 plus 35, these are base 6 numbers. And so when you add 5 ones and 5 ones, we do get a total of 10 ones. Oops, that is large. There we go, we get 10 ones. And these are in the 6th position, right? This is base 6, right? So these are the ones, these are the 6s, and these are the 36s. So when you had 2 6s and 3 6s, you get 5 6s and 1 36. So this is what we have, just 1 5 10. But 10 ones in base 6, every 6 ones combines to be a 6. So we have to take 6 away from this 10 and convert it to a 1 in the 6th column. So now we have 6 in the 6th column, 4 left in the ones column, and 1 36. But 6 sixes makes 1 more 36. And so remember, in base 6, it's groups of 6 that collapse and become a single dot in the next higher place value. So this 6 needs to convert to another 1 to join that 136 over there. So we have 2 36s now, no 6s left, and 4 ones. And this is how you want to leave your answer. Keep in mind that this is base 6. So 2 36s, no 6s, 4 ones. That's a total of 76 in base 10 if you wanted to convert it. Now we're going to use a standard algorithm to do operations. 36 plus 87. What happens here is effectively what happened up in this position here, except that we don't allow for 2-digit numbers to exist in a position. We do the collapsing of and converting to a digit in the position of greater value. We do that right up front. That's all that's happening that's different. So for example, if we say 6 plus 7, that makes 13. We'll keep the 3 ones, but the 10 from the 13, we're going to group with the other 10s. In other words, bring that 1 up there. put it in the tens position. Now add all these tens together. We have 1 plus 3 plus 8. So we get 1 plus 3 plus 8 is 12, but really we're adding 10, 30, and 80, and we get 120. So we put the 2 there, and then carry a 1 up into the hundreds position. And then, of course, that 1 is nothing to add to, so it just drops down. Some will say that if you're at the end process of this and you get a number that's a 2-digit number, you just finish by putting that 2-digit number there, same difference. But this is not a 12, mind you. This is a 100 and a 20, so it's 120, or 12 tens if you want to think of it that way. Place value matters here. It's a child who does this, who learns this way, thinks that you're really just adding, may think that they're really just adding 1, 3, and 8, and not realize that you're truly adding 10, 30, and 80. Hence, math feels magical. You get this 12 with a 3 next to it, and somehow this now means 123. It's super valuable to a student, a learner early in the process, to use place value tables and or these base 10 blocks, so they truly have a sense for the quantities that they're adding when they do a more efficient algorithm such as what you're seeing here. In the case of subtraction, similar, there's going to have to be some borrowing, right? There's 8 ones in this box and 9 ones below it, and I can't remove 9 from 8 unless you want negative numbers, which we're avoiding right now. So we're going to do what we traditionally call borrowing. We're going to get rid of one of the tens from our tens position. We have 4 tens here, so there's a 40. We're going to make that a 30 instead, and then add that extra 10 to the 8, so that turns it to an 18. Now compare digits, right? 9 is underneath the 18, so that we can remove 9 from 18. We can't remove 5 from 3, so we'll have to do some more borrowing. We can do the borrowing right now to position everything for subtraction. So let's do the borrowing now. I'm going to go from 500s down to 400s, and the extra 100 I'm going to tack on right here and make 10 tens. So changing 3 to 13, I actually changed 30 to 130, so that 100 went into that position. And now look vertically column by column. 4 is more than 2, so I can subtract those. 13 is more than 5, so I can subtract those, and 9 is more than 18. Sorry, 18 is more than 9, so I can subtract those. And now we can just do digit or column by column. 18 minus 9, 18 dots minus 9 dots, or 18 ones minus 9 ones gives you 9 ones. 13 tens minus 5 tens gives you 8 tens, and 4 hundreds minus 2 hundreds gives you 2 hundreds. Notice what I'm saying. I'm not saying 4 minus 2. It's better to actually use words that represent what this 4 and 2 are. You should say 4 hundreds minus 2 hundreds. That helps reinforce the value of those represented by those numerals. Okay, so this next problem, explain how you could perform each operation in 3 different ways. Somewhere on this page, you should demonstrate each of the item in the table below at least once. So I went the number system. I numbered them 1 through 3, 4, 5, and I just said, hey, I'm doing item number 3 here, for example. I found that to be a nice way to communicate this. So point out exactly once in your work where it was demonstrated, even though you might demonstrate it multiple times. You might use item 2 multiple times, but at least point it out once is what I'm getting at here. For example, somewhere in your work, state once I use the commutative property of addition here. Okay, so 56 plus 89. We could do this with place value tables or the standard algorithm or base 10 blocks, but here I'm talking about different strategies, not different models. So strategy to add 56 and 89. Well, what would be added, what would you want to add to 56 to make it a nice multiple of 10? And the answer to that is 4. So I'm going to do a decomposition of 89 into 4 and 85. So I'm going to go ahead and point that out right now. I did item 4, which is a decomposition of a number. Then I'm going to do the associative property. So my next line allows me to add the 56 and 4 together first, as indicated by the parentheses, the shift in parentheses. So going from this line to this line, I've used the associative property, so I pointed it out. 56 plus 4 makes 60, so we combine those together first to get that 60 right here. Then, let me zoom in a little bit. Then I'm going to decompose. Maybe you could argue you don't need to do this, but why not? I decomposed the 85 into 80 and 5 because I found it easier to add these together first to make 140, and then we have this 5. In the end, oops, we get this 145. So there's one way to do this. Another is to decompose the 56 instead by asking yourself, hey, what would you want to add to 89 to make it a nice multiple of 10? And the answer is 1. So I decomposed 56 into 55 and 1. Then I used the associative property again, added the 1 and 89 to get 90. And then if you want, you could decompose the 55 and do more addition, or if you're comfortable saying, hey, what's 55 plus 90, and getting right to 145. Third way, 89 is close to 90, so I could add to 56, here's 56, add to it 1 too many, but then take away that 1 too many. So adding 89 is like adding 90 minus 1. This is a sort of a form of decomposition, if you will. It's expressing 89 as 90 minus 1. But then add 90 to 56. That's easy to do. You get 146, but then remove the 1 from that, and that also takes you to 145. So when doing this, there's probably more ways you could invent. You could use number lines and other representations or strategies for getting an answer here. Me giving these 3 different strategies isn't me trying to tell you that these are the only 3 or the 3 I was looking for in your work, right? There are multiple ways of doing this, which is why we have group work, because it's very helpful to see, hey, I did it 3 ways and I can't think of any more, but person B did it 2 ways I didn't even think of. And so it's nice to do group work and see a variety of strategies. Let's do the adding multiple numerals. 14 plus 8 plus 6. Well, I noticed that if I were to add 14 and 6 together, then I could get a nice clean 20 and then add 8 to that. So I'm going to do a little bit of, I'm going to use the commutative property to switch the 8 and 6 around, right? So I'm pointing it out because I haven't pointed out the commutative property of addition yet, so I point it out here. And now I'd use the associative property to get to this line, and then from there add the 20 and the 6, and then add the 20 and 8 next, and you get our 28. Another way is, because addition is associative, you don't really need the parentheses in the first place. There's a lot of freedom here, so I just got rid of the parentheses. I decomposed the 8, and then I just thought of this as a multiple step process. I liked decomposing the 8 because adding this 6 and 14 seemed like a good first step. So that's why I chose to decompose 8 into 6 and 2 in the order that I did. And then I'm going to use a number line to illustrate this advancement, or this change of 14 into a new numeral. I started with 14. I added 6, that took me to 20, and then I added 2 to that, took me to 22, and then added 6 more to that, took me to 28. And so here's a demonstration of using a number line as a way to help organize your addition. So I pointed that out as item 5. And I think I've pointed out everything. I've done 1, 2. I haven't done item 3 yet. That will have to do that on the third example here. By third example, I mean looking down here at this subtraction. But as a third strategy for doing the second example, I decomposed well, actually, I added the 8 and 16 together. First got 14, so I had 2 14s, and I decomposed them both into 10 and 4 and 10 and 4. And then I did some commutative properties here. Like, for example, I commuted this 4 and 10, switch those around. So I have the 10s together and the 4s together, which I represented by these sort of lines that telling me what I added together first. Right, the 10s I grouped together to make 20, and the 4s I grouped together to make 8, and then grouped those together to make 28. All right, let's do the subtraction. 91 minus 38. I began by thinking, gosh, it would be nice if I had 98, because removing 38 from 98 is nice and convenient. So I did a form of decomposition by writing 91 as 98 minus 7. So I have 98 minus 7, and I'm going to remove the 38 from the 98 first. Ask yourself, is this allowed? If you have a certain amount, 98, and then you remove 7, and then you remove 38, does it matter to you if you remove those same 2 amounts but in the opposite order? The answer to that is it should not matter. Right? If you're doing subtraction and then more subtraction, it doesn't matter which order you do the subtraction in. Now, that's not me saying that subtraction is commutative, right? To say subtraction is commutative is to suggest that 5 minus 3 is the same as 3 minus 5, which we're going to see is not true. Subtraction is not commutative, but when you're doing subtraction twice, right, if you have 5 dots and you remove one of them, and then you remove 2 of them, and you see what's left, right? The order in which you did that removal doesn't matter. Remove the 2 first, then remove the 1, and you still are left with 2, right? So me saying that it doesn't matter the order in which you remove the 2 things, that is not saying that subtraction is commutative. So be careful about that. Don't interpret it that way. So removing 38 from 98 was rather simple. The 8's remove, and then the 90 minus 30 gives you 60. So we just have 60 sitting there. And then removing 7 from that is easy to get 53. So here's one strategy. A second strategy is I'm going to start with this 91 minus 38, but I'm going to decompose 38 into 1 and 37 and remove them piece by piece. The reason I picked 1 and 37 is because removing 1 from 91 is convenient. And right here, when I decomposed 38 into 1 and 37, I did need to have it in parentheses because you're removing both parts. Right? To remove 38 is like removing 1 followed by removing 37. And so when I remove the parentheses, I need to write subtraction twice. This is the distributive property of subtraction, which is item 3 in our table here, and I'm demonstrating it and pointing it out right here at this stage. So I'm going to remove 38 by removing 1 and then removing the rest of the 38, so removing the 37. 91 minus 1 takes you to 90. Now we've got to remove 37 from 90. So I'll do some more decomposition and then some more distributive property of subtraction. I'm going to decompose 37 into 30 and 7, and then remove them separately. Remove 30, then remove 7. And 90 minus 30 is 60, and now remove the 7 more, gets you also to 53. And then the final strategy here, I'm going to do this idea that since 38 is close to 40, if I want to remove 38, then I can remove too much. Remove 40, but then put 2 back. That's the equivalent of removing 38. Right? So remove 40, but then put 2 back. And removing 40 from 91 is easy to do in your head. It just takes you to 51, but then put 2 back and you get this 53. So here's another strategy you might do when you're subtracting a number that's close to a multiple of 10. Right? 38 was close to 40, so just remove 40 and then put 2 back. And again, on this problem overall, here's 9 total strategies are depicted here, and you might have 9 different ones than what I have, and that's fine, as long as they're valid strategies that you can justify. Question 4, give an example of a missing addend addition task, a word problem. Then solve the task while explaining your solution. Do not use any example from the lecture, right? I just want you to copy things from the lecture. Come up with your own situation. So what I have here in my solution is going to be obviously very different than what you might have. But John drove, I'm going to go with this one. John drove 12 miles, then he drove some more, and his odometer said he drove 15 miles in total. How much more did he drive? All right, so the structure here is this is a missing addend problem because he went some amount, 12, plus some unknown amount, and his total was 15. So this is an additive structure with a missing addend. So I put a box for the missing spot, or you could put a question mark there, or a blank space, or a line, or you could put an unknown, a letter to represent an unknown. We'll use an X here. So we're trying to figure out what X is, so that 12 plus X is 15. And subtraction will solve this for us. If we do 15 minus 12, we'll figure out what that missing addend is, and that turns out to be 3 miles. Notice I left units off until the very end, but I have a final answer here. Always keep a unit. If I say the answer is 3, again, that's meaningless. 3 what? 3 kilometers, 3 feet, 3 pigs? You have to say what the 3 is referring to. Don't ever assume that the reader is putting the same unit on there that you are. And I decided also, I didn't really say to do this, but I decided to also model this missing addend task with some sort of structure here. For example, we have 12 miles represented by these 12 blocks, and we know that we're going to add something to it, right? Some unknown amount I'm going to add to that so that we have 15. Well, this is nice because if I start with the 15 and I remove this amount here from the 15, oops, I didn't mean to grab the red as well, remove that from the 15, the question is what's left, right? So, remove. I'm going to remove all of these, and you can see very clearly that we have 3 left over using this model. And that answers the question as to what we should add to 12. Right, this question mark should be 3 blocks, is what we want to add to 12 blocks to make 15 blocks. But this helps show that why subtraction is a model for solving a missing add-in task, or why subtraction works when you want to solve a missing add-in task. Next one, give an example of a missing sum addition task. Then solve the task while explaining your solution. Do not use any example from the lecture. I went with June drank 5 cups of water before her race and then 7 cups after. 7 cups of water, to be more precise. How many cups of water did she drink in total? So this is, she drank 5, then she drank 7. This is you want to combine 5 and 7 to get a total. So this is a missing sum task. We know the two add-ins, but we've got to figure out the sum. And so the adding 5 and 7 is like, right, combining 5 with 7, and you have a new amount, and that's total is 12 cups. Explain a scenario where 2 plus 1 is 6. Then explain the assumptions for which numerical addition produces expected answers, such as 2 plus 1 is 3. Now, if you were to just say, hey, 2 plus 1 can be justified and proven to be 6, most people would scoff at that because they don't realize that to say that 2 plus 1 is always 3, that you're making an assumption about the numerals and what they are representing. These assumptions are so ingrained that some thinkers don't realize they're even making them. But I could justify that 2 plus 1 is 6 depending on what reference I put on these. And you might come up with a different situation, but the one I came up with was 2 quarts plus 1 gallon. Now, a gallon is measured in quarts. It's 4 quarts. So if you take 2 quarts of a liquid and you add 1 gallon to that, it's perfectly reasonable to say that you now have 6 quarts. So I've justified that 2 plus 1 is 6, but I can only justify it by having different reference on the values. If we want to be able to say that 2 plus 1 should always be 3, then we have to say that the 2, the 1, and the 3 all have to have the same referent. And with that assumption, then it is consistently true that 2 plus 1 will produce 3. 2 of something plus 1 of that same thing will equal 3 of that thing, is a good way to say it and think about it. Question 5. Give an example of a missing minuend subtraction task. The task should imply the takeaway model for subtraction, then solve the task while explaining your solution. Do not use any example from the lecture. So missing minuend is the thing you subtract from. So like 5 minus 2, 5 is the minuend, and we want that to be missing. So we want to have some sort of starting amount that we don't know, but we know how much we remove because we're doing the takeaway model, and we know how much is left. That would leave a missing minuend task. So I went with Gwen and some money. Gwen gave $6 to her friend. Now Gwen only has $11. How much did she have to start? So this is a missing minuend task because I don't know how much she had to start, but I know how much she took away, and I know how much she has left. So in our structure here is some unknown amount minus 6 should produce 11. And we solve this task through addition. We would put the 6 back to the 11, add the 6 and 11, and see how much she had to begin with. And that's going to give us $17 is what she started with. So this is kind of like if I were to model this with some bars. So we have some unknown amount. I put a question mark for the entire red bar. But I know that we're going to remove the red 6. Right? We're going to take away this 6 and ask, and the resulting amount needs to be 11. So if I put them side by side, I know that if I take 6 away from an amount and what's left is 11, then it should make sense that what we had to begin with was to add 11 and 6, right? And so 11 plus 6, or this total amount here, should be what she had to begin with. So that when you take 6 away, you're left with 11. So this is a good visual for understanding why you solve a missing minuend task by adding the subtrahend and the difference. Let me say that again. To solve a missing minuend task, you solve it by adding the subtrahend and the difference. The subtrahend was 6, the difference was 11, and you added those and you got the missing minuend. Give an example of a missing subtrahend subtraction task. Again, a word problem. The task should imply, again, the takeaway model for subtraction, then solve the task while explaining your solution. Mark had 13 marbles, so this time it's how much we remove, we don't know. That's the subtrahend, but we know how much we had to start, and we know how much we have after the removal. So Mark had 13 marbles in his pocket. His pocket had a hole, and 10 minutes later he had only 8 marbles in his pocket. How many did he lose? Well, he had 13 minus some unknown amount, and he has 8 left. So this is a missing Subtrahend task. And it's also resolved by doing, it's going to be resolved by doing subtraction this time, which is not how we resolved this missing minuend task. We added the subtrahend and difference to get the minuend, but to solve the missing subtrahend task, we're going to do the minuend minus the difference. So it feels like there's a different strategy at play here. And we want that to make sense of why that is the case. Why do 13 minus 8 to get that 5 marbles were lost? Well, I'll do these dots too. Here's the 13 dots that represent the 13 marbles, and then 10 minutes later he only had 8 dots left, 8 marbles left. So the question is, how many were removed? Well, if I start with the 13 and I remove the 8 that he has left, like safeguard them, and then this allows you to see how many were lost. So the minuend, which is 13, remove the difference, and it gives you the subtrahend. Right, that should feel like a very sensible thing when you look at a visual of these, a representation of these marbles. Now, I suppose you could generalize and say, hey, you always solve a missing minuend task by adding the subtrahend and the difference and turn it into some sort of rule. But the problem about rules is when students memorize rules and then use them, they don't necessarily have a conceptual foundation that lends plausibility or credence or reasonability to the rule. It's better that students have a conceptual foundation and that they produce rules themselves based off their conceptual foundations. Rules should never be taught in place of understanding, as a replacement of understanding. And I suppose you could make a rule that says if you're trying to solve a missing subtrahend task, you can always solve it by subtracting, doing the minuend minus the difference to solve it, and make some sort of rule there. But again, just the caution about rules remains in effect. Give an example of a missing difference subtraction task, a word problem. The task should imply the comparison model for subtraction. So nothing's going to be taken away. We're just going to have two amounts that we're going to compare and use subtraction to establish that comparison. Then solve the task while explaining your solution. So we need to have two amounts that aren't going to change. So let's say that, and the difference is unknown. So let's say that Alex weighs 60 pounds and May weighs 73 pounds. How much more does May weigh? So when you're doing comparison, you would take the larger amount and remove the smaller amount, and that gives you the difference. And that difference can be used as a comparison. And I said the word takeaway. I shouldn't really do that. We do the subtraction, but nothing's actually being taken away, right? You don't take weight away from Alex. You don't take weight away from May. Their weights remain unchanged. But we can still think that I'm going to take weight away from weight to get the difference, to get the comparison. And 73 minus 60 would be our subtraction, our difference. It's the comparison model for subtraction, and it gives us a total of 13. So 13 pounds is the difference. This is why we use the word difference, by the way, for subtraction when you're comparing. How do these two people differ in weight? Well, May is 13 pounds more than Alex, and that 13 is called a comparison. No weight was taken away from either person, but they do have 13 pounds of difference in their weights. And why you could think of removal as a way to model this comparison, right? If Alex's weight, line it up with those 10s there and then remove them from May, right? Remove those, and what's left, right? When these 60 are removed, you can see that the difference is this 13. But again, physically, no weights are actually changing here. Nothing's actually being removed, physically removed. And number 6, the last task here. Miguel drew the following for calculating 19 plus 15, explain a strategy, and express his steps symbolically. So he's trying to add 19 and 15, and it looks like, if looking at this work here, they added 1 first, then he added 15, and then he subtracted 1. So I'm going to write this symbolically. Does this make sense that you can do this? Well, adding 1 and then 15 is like adding 16, which is we added 1 too many. So that's why removing 1 makes sense as a final step, so that we have an equivalent of just adding 15. So symbolically, I represented it this way. 19 plus 15, we're going to add and subtract 1. So that's having no effect. Add 1 and remove 1 is like you did nothing different. So 19 plus 15, and then add 1, subtract 1 is the same thing as just 19 plus 15. But then I'm going to do the commutative property of addition and add the 1 first before the 15. So we do 19 plus 1 first. That gives me 20. Then I did the 20 plus 15 to get the 35, and then I finished with the minus 1 to get the 34. So here's a good symbolic, the steps that represent symbolically what I see depicted here in this image. June drew the following image. What single operation was she attempting to calculate? What strategies and or properties did June use? All right, so because of the pluses, it seems like June is adding these amounts, right? If those had been minuses, then I might have thought that June was going backwards. But pluses suggest that she was starting at the 31 and arrived at the 56. And she did it by adding 10, and adding 5. So it seems like the original operation she was doing was trying to add 25 to 31. And then she did it by decomposing 25 into 20 and 5, and then further decomposing 20 into 10 and 10, and then doing this one at a time. 31 plus 10, and then 41 plus 10, and then 51 plus 5 to get to 56. And lastly, Rebecca decided to solve 18 plus 29 by rounding both numbers up to friendly numbers. Show what her first step might look like, then finish the problem in the way you expect she might. Model your steps on a number line. So rounding 18 up to 20 is like adding 2, and then you need to remove 2 so you don't change the value. So in other words, I'm going to add that 18 and 2 to make this 20. In other words, changing 18 into this 20 minus 2 is a form of decomposition. Changing this 29 into 30 minus 1 is, again, a form of decomposition. And then doing the positive terms, add them together. So add the 20 and the 30 first, and then do the 2 removals second. So changing 18 to 20 and 29 to 30 introduced 3 values that we need to remove. So we wind up just doing 20 plus 30, but then remove the 3, and then that gives us to a nice clean 47. So visually it looked like this. I rounded 18 to 20 by adding 2, and then I added 30. But adding 30 was 1 more than adding 29, so I had to reverse this 2 that I added, so there's the minus 2, and then adding 30 was 1 more than what I should have added, so I had to remove 1 as well. And you can see the process here. 18 got add 2 to 20, and then we added 30 to 20 to make this 50, and then we removed 2, and then removed 1 to get to 47. Now you might have a slightly different explanation than I have here, but this is just an example of one way that Rebecca might have attempted this problem.